Hello! In the second video of our series on Kirchhoffs laws, we will be addressing Kirchhoffs' second law, which is also known as the loop theorem. Kirchhoffs' first law and second law constitute an important foundation for the calculation of currents and voltages in more complex DC circuits. So, what is Kirchhoffs' second law all about? It states that if you have a closed loop in a DC circuit or subcircuit, such as this one, that the sum of all voltages and voltage drops along that loop is zero. If you have a starting point somewhere in your subcircuit, such as here, and you run along the loop back to that point, the sum of voltages and voltage drops on your path will be zero. Before I spend some more words on that law, let's clarify what a mesh is. A closed loop in a circuit or subcircuit is called a mesh. I have a scheme here of a circuit where the rectangles represent subcircuits. I have intentionally not drawn any resistors or voltage sources to keep the scheme simple. If I have a starting point, again, and I run along the small subcircuit back to the starting point, I have a mesh. Let me label that mesh as M1. Okay, I can also run around this mesh, which encloses two of these subcircuits. That would be this mesh, and I will label that as M2. Then I can have this mesh covering these subcircuits. It's gonna be M3. And then I can also have the big mesh. It's getting a little messy here. The big mesh will be labeled as M4. So, these are all possible meshes in this circuit. However, you should know that if you have a mesh, each wire or each node must be passed through only once. For example, you cannot have this path as a mesh, so starting here and then going this way. Let me actually draw that. So you cannot have something like this. Because then you would run through this wire twice, and this is not allowed. Also know that it is standard to have clockwise meshes, and the current is assumed to flow in that direction. Now, let's get back to this circuit. To give you an analogy of Kirchhoffs' second law, let's look at mechanics. If you are on a mountain and you run a loop on the mountain where you encounter upward and downward slopes of different intensities, it is plausible that the sum of all upward and downward slope distances must be zero, because you go back to the same height where you started, don't you? So, same thing with a circuit, where the heights represent electric potentials and height differences, voltages or voltage drops. So, this is my starting point, and I have a clockwise mesh in the circuit. Along the closed loop, I encounter a resistor, a voltage source, and then some more resistors and voltage sources. Let me now set up an initial equation that reflects Kirchhoffs' second law. Starting at the starting point and going clockwise along your closed loop, if I encounter a resistor, like R2 here, I treat it like a voltage drop. So in the equation, I write down minus U2. Next on my path is a voltage source. Now, if on my clockwise path, I first hit a negative pole and then a positive pole of the voltage source, I treat it sort of like a voltage booster, which adds voltage, so I put plus US2, and S stands for source, the source voltage, basically. Next is the resistor R3. So I write down minus U3, because this is the voltage drop across the resistor. And now I have another voltage source. However, be careful with where on the voltage source you have a positive pole and where on the voltage source you have a positive pole and a negative pole. Previously, we had a negative pole coming first and then a positive pole on the path. So we treated that voltage as positive. Here, on the other hand, you encounter a plus pole first and then a minus pole. This means that the voltage source is directed against our clockwise direction. So we treat that voltage source as a sink, which makes it negative. So it's gonna be minus US1. And by the way, let me label these voltage sources. Okay. So, and at last, I have this resistor on my path before reaching back the starting point. So this resistor has a voltage drop, and that voltage drop can be expressed as minus U1. Now, that whole thing must be equal to 0 because we are ending up at the same point where we started. And there's no difference in potential at this point. So the sum of all voltages along the mesh is 0. And this can also be expressed as the sum, I'm using the Greek letter sigma, the sum I equals 1 up to n, the sum of all u's, ui's is equal to 0. Now, how do you calculate the voltages? We don't have any specific numbers yet, but we will have them in the second part of the video. However, you can calculate the voltages by simply multiplying the current by the resistance for each resistor, such as U1 is equal to R1 times I. Okay, we hope that we could explain the basics of Kirchhoffs' second law, and in the next video we will work out a mathematical example.